Okay, so I was testing a little bit. Seems like it's manageable. If I am faltering at places, you are there to help. So, um, so today, ideally, we were supposed to start dynamic programming, but before that, like I thought of talking a little bit more about the graph traversal things that we were doing, and this was also continuing in last week's lecture, I would guess, where you have probably learned about pre-order, post-order, and in-order traversals in more details on binary search trees. So one thing that I thought of would be a nice example, I mean, an end-to-end example was your lab assignment on the topological sort problem that we gave you last week. So there was this idea of you know uh, people beating each other, or let's say agents. Oops. Oh, this is a trouble.
Sir,
Yes.
sir, there is a problem with the Teams whiteboard that when you record the class, the whiteboard doesn't get recorded.
So that's why I was telling, you did not object when Sharup wanted me to do it on whiteboard. None
Yes,
of you pointed this out.
so this thing did not came to my mind. Like I did not remember that this is the problem with
So
whiteboard.
let me go back to the old setup.
Yes, sir.
Should be able to see my screen, right?
Yes, sir.
Okay. Hmm. Okay, so now let us. Hmm. So the last day's assignment, if you recall, we were doing, we were asked to uh, like check whether um, like a winning sequence is possible or not. Okay? And people can beat each other with some constraints, and you can beat people if you have already beaten those that, or beat, let me call it a person, that would be easier. You can beat a person if you have already beaten those that this person has beaten. So you can understand that this would be a nice directed graph formulation where, like, if A beats B, then you have a directed edge from A to B. Okay. Similarly, like if B beats A, then you can have a directed edge from B to A. But more than this is not possible by the constraint that was there in the question paper. So more than this is not possible for a particular pair. Now you can understand that in order to, I told you in the class also, in the lab hours also, that solving this problem would require you to do topological sort. Okay, topological sort of the graph formed by this kind of edges, where edges indicate like someone beats someone else. So you have directed edges, and you have to do a topological sort to find out if there is someone whom you can start beating, who has not been beaten by anyone, and whom you can start beating with and then continue. Okay, so this is exactly the topological sort requirement. So, but the question was given that you have to do the topological sort using a BFS queue. Use a BFS queue to perform the topological sort. That was the requirement. Now, this algorithm was due to someone called Kahn, and we call it Kahn's algorithm. But this is a very easy approach, as you will see. And this I had already taught you in the class. So can you tell me what idea we will leverage here? Like, what idea have you leveraged? Let me listen to those first. How have you approached the problem? No one has any answer? You did not approach the problem?
Sir, I created an array which will be containing the integrity of all the nodes, and then I will
Yes.
be enqueuing the nodes which have degree 0.
Very good. So
And
it's
then, yeah,
that greedy in degree algorithm, right? That we discussed in the class.
yes, sir.
That's what you have used. Yes, exactly. That is what you will have to use. So I'll give you the steps here, and then like any variant of this kind of an algorithm is acceptable. So this is like end-to-end way of attacking a problem. So compute in degree of all the nodes. Initialize total node count to 0. Now, step 2, pick all nodes with 0 in degree and NQ them to a queue. Say, let's call the queue temp. This is a temporary queue that we are maintaining. Now step 3. DQ a node do the following. NQ the node in result queue. Total node count plus plus. Decrease in degree of all its neighbors by 1. If any of its neighbors in degree is 0, add it to the temporary queue. Now, step 4. Repeat step 3 until temp queue is empty. Okay. Step 5. If total node count is not equal to 0, then what will you infer? What will you do? There are some steps. Sorry. Tell me what to do if total node count is not equal to 0.
Sir, the value of total node count will be changing every time we DQ a node and NQ it in the result.
Exactly. So if it is finally not equal to 0, then?
Sir, it should be not equal to n, right? Because it is increasing total node count.
First of all, non-zero. If it is 0, then what? It is 0. That is also possible, right?
Yes.
Is it possible that it is 0? It is just
Yes,
0.
Sir.
Yes.
So that means this condition needs to be checked. If it is non-zero, then you check if total node count not same as total number of nodes. Then topological sort not possible. Else what to do? DQ
The result queue.
the result queue. To get the topological sort. Okay, so that's all. This is what we'll have to do. Now let us take an example. One example, let's take, which is like a extreme boundary condition. So these are the integers. So what will happen here?
No
Sir,
topological sort.
No
yes.
topological sort. Since there is no node with 0 in degree. Okay. So similarly, you can construe examples one by one, and you will see that this algorithm will definitely give you the desired result. Now, there was another question, okay, where you had to find out that what is the number of games that could be allowed. Okay, so how does that problem translate to the graph question?
Sir, it is maximum number of edges that can be added without making the graph.
Absolutely, yeah. So it is the maximum number of edges that can be added, okay, without introducing a cycle, right? So how do you find out the maximum number of edges? Okay, starting from a specific node, say you can also compute all of them. Both are possible. So let us say we have a graph structure like this. And then there is a dangling node here. So now in this graph, there are at least 2 nodes within degree 0. And therefore you can, of course, start the topological sort. And you will see that topological sort is actually permissible for this graph. Okay, so you can have multiple such topological sorts, and one of these would be the following. Fine. So this is one of the topological sorts. There could be multiple, because there could be multiple nodes which are becoming degree 0 after the removal of a particular node, and therefore there could be multiple like topological sorts. I'm taking one example. Okay. Now, what do you do to get, say, the uh, max number of edges from A without introducing cycle? How do you get this?
Sir, any element in the right of the
Absolutely.
if we
Very
have
good.
no
Very
edge,
good.
then we add an edge.
Yeah. So basically, if you look, all the candidates to the right of this topological sort are okay candidates to which edges can be added. Okay, but then in your original graph, if you check back, in your original graph, we already have the AB edge, we already have the AC edge, we already have the AG edge. Okay, so AB, AC and AG are already there. So the other edges that could be added without introducing any cycle would be then A to H, A to E and A to F, right? So these are the total number of edges that could be added to the network in order to maintain that there is no cycle introduced, if you are considering A as the source point from where you are adding the edges. Okay, and what is the maximum possible? Maximum possible edges. How do you compute that?
Sir, can it be NC2, sir?
No, maximum possible edges that can be added. I mean, what will you do that for that?
So we will keep
Simple.
on counting the.
Extend this same idea. So from A, all rightward edges. Okay. All rightward edges from A. Similarly, from H, all rightward edges. Now, since you have an ordering, you can have this right left notion, right? From G, all rightward edges. Again from C, all rightward edges. It is becoming a bit clumsy, but I guess you are understanding what I'm trying to say. Okay, so these are the maximum possible number of edges that could be added to this DAG without introducing any cycle in it. Okay, so this is how you try to solve a problem end to end. Okay, so now we will start whatever we had to start today. So today we will try to get introduced to this idea of dynamic programming. So I think, like you recall, that in the initial lectures when I was teaching you about complexity analysis, we talked about the Fibonacci problem, and there we showed a very inefficient implementation, and then we went forward to a more efficient implementation. And this efficient implementation was something which like builds on the notion of dynamic programming. Okay, so what is the basic crux? So here also you divide the problem into subparts. Okay, now the smaller instances are related here. Okay, and this is what is the major difference from the divide and conquer approach. In the divide and conquer approach, the smaller instances are unrelated. Okay, so this is the primary difference in a dynamic programming framework or in the dynamic programming paradigm. All problems will have a situation like this where the smaller instances are related. Okay, smaller instances are related, and therefore that allows or facilitates the solution of the larger instances, and this is in departure from the divide and conquer approach where the smaller instances themselves are unrelated. For instance, say in merge sort, you have to separately sort the two parts that you divide, and then you will have to merge. But here, when you divide something into a subpart, then the subpart will add to the overall solution of the problem. Okay, so this is also, we will come to know more about this as we proceed. This is also called the optimal substructure. So if a problem has this optimal substructure property, then only you can solve it using a dynamic programming approach. So the feasibility of a dynamic programming approach depends on whether your problem has an optimal substructure or not. That is the first thing that one needs to decipher. Now, going back to a little bit of history of dynamic programming, why such a strange name? Why dynamic programming? Anyone knows? Anyone knows about why it is called so? Okay, let me tell you. So originally, dynamic programming problems emerged a lot in control engineering. Okay, in control engineering, especially in the EE sciences, dynamic programming problems were very frequent. So, and many of these problems had dynamical systems related to them. Okay, so as you understand, like if you have like some idea of control systems, you will see that there is a lot of dynamicity or dynamical like properties of such control systems, and that's how the word dynamic came into this algorithmic paradigm. And programming here means, this is a very important point. Programming here means to maintain a table. So all dynamic programming algorithms function by maintaining a table where you store the solutions to the sub-problems and you intelligently use it when you need to solve the bigger problem. So you basically store the solutions to the sub-problems which are used to solve the larger problem. So if you think of a divide and conquer approach, what type of approach it is? How does it break the problem and solve it? What is the direction of solution? What is the direction of solution?
Divide, conquer, and combine.
Yes, so that is also something like a top down approach. Was this told in the class? Was this told in the class? So say you have an array. Okay, so you are as if looking at the problem from the top. So now you break the array. You further break the array. So this is a top down, going from top to down. Okay, that's why top down approach of solution. Okay, what about dynamic programming?
Sir, I think it is a bottom to top.
It's a bottom up approach. This is called a bottom up approach. Why bottom up? Because first you get the solutions for the smaller problems, smaller sub problems.
But sir, even in
Solution.
divide and conquer, we first solve the small, it base cases and we go up by combining them.
Yes, yes, true. But then your problem view is from the top, right? your problem view is from the top. Agreed? Here, as you will see, I'll tell you why this is so. The smaller subproblem solution is obtained first. So the notion comes from the table. If you look at the table that you start filling up, so can you tell me, so in the top-down approach, let's draw it in like parallel. You had a view like this, right? While solving.
Yes, sir.
Okay. You had a view like this. In the DP solution, when you build up the problem, okay, guess from where you will fill up the table.
Yes, sir, from bottom.
From here. From here, you will start filling up the table. Okay. And your solution to the problem will lie here. You will keep on building, filling up all these entries, and all these entries will accumulate and give you the solution here. The 0, 0 is your solution. Okay. And the NN is the place from where you start solving the problem. So this is why this has a bottom-up structure. Okay. Okay. So with this preliminary points in mind, we can now go to the 2 important steps of any DP. The first step is you have to establish a recursive property that gives the solution to an instance of the problem. Okay. Now solve an instance of the problem in bottom-up fashion by solving the smaller instances first. So these are the 2 primary steps. Okay, these are the 2 primary steps to obtain a DP solution. And as you can understand that establishing or producing this recursive property is the most important part in this whole game. So in a DP, if you are able to set up the recursive property correctly, then all your problem is done. After that, it's a table fill up and table lookup, right? So the most important thing here is to construct this table or the table entries using the recursive property. And this recursive property in turn can be obtained by thinking in terms of the optimal substructure. Okay, you have to think what are the similar substructures that are useful in solving the original equation. For instance, the optimal substructure for the Fibonacci series was this. Okay, and now you can start filling up your table. Fine. So the optimal substructure is something that you need to compute. Okay. And from there,
Sir,
yes.
optimal substructure means the problem with smaller instances?
Yes. Yes. That's what I said. Right. So if you recall, we just discussed that smaller instances, okay, basically optimal substructure will tell you how combining the smaller instances results in the bigger instance or results in the solution to the bigger instance. Okay, that is what is finding optimal substructure. So hunt for optimal substructure. This literally means that how does the smaller instances combine to give the solution to the larger instance. Okay, so this is what you want to identify. Now we will take up one problem to start with. We will see many examples of DP. So I will talk about two large examples of DP, and then Vishal will also talk about the last year's DP lab problem, as well as I have requested him to talk about one another very interesting DP problem. Okay, so the one that I am talking today is a very important problem. We will not be able to like complete this, but again, in graph theory, this is one of the problems that, like cycle finding and traversal, are something that like are kind of indispensable part of any, say, graph theoretic course or any graph theoretic application. So is this one, and this is called shortest path finding. So remember the definition of path that I taught you. Remember what is a path? What is a path?
Open walk in which no vertices are repeated.
Yeah, open walk with no vertices repeated. Also remember what is length of the path? What was the length? It's the number of edges in that path. Okay. Now, if it is a weighted graph, what will be the length?
So sum of weights of all edges.
Sum of weights. Now, suppose I'm given two nodes. In a graph, which one is true? Many paths are possible, right? Between a pair of nodes. Okay. And for each of them, you can calculate the length
Sir,
Now,
how can we say that many paths are possible?
many
It can
paths
be
are not
only
possible.
two. If
It can be
directed
only.
two, if
Okay.
only A and B are there, and it is
Okay.
directed.
Let's see.
Yes, sir. If there are three, if number of nodes increases, then it will increase.
That is what I'm telling. So I'm just telling that suppose some arbitrary nodes in a graph. This is a path. This is a path. This is a path, right?
Yes, sir.
This is another path. So there are multiple such paths possible between a pair of nodes, like given an arbitrary graph. Okay. So now you can compute the length of each of these paths. Now the shortest among all this is the shortest path. So shortest path is the path between a pair of nodes with the shortest path length. Okay. So shortest path is the path between a pair of nodes with the shortest path length. Now, question is this unique?
Sir, it depends on the original configuration of the graph.
In general, for any arbitrary graph, is this unique? I mean, is it mandatorily unique?
No, sir, I don't think it should
No,
be.
sir.
And you can find umpteenth examples of this. Okay, just giving you one example. Think of a complete graph. Okay, how many shortest paths are possible between a pair of nodes? Complete graph. Remember what is a complete graph? Every pair of nodes are connected by an edge.
Sir, then if the wets are same, then we can say
No
that.
weights. Say weightless. This is an undirected, unweighted graph. How many shortest paths are possible between a pair of nodes?
Sir, if there are k nodes, then k minus 1 paths are
Yeah.
possible.
So n minus 1 nodes, n minus 1 paths, right? And all of these are shortest. So just to give you a trivial example where you can show, whereby you can show that the shortest path is non-unique in a general graph. It's mandatorily, it need not be mandatorily unique. Okay. So now the algorithm that we are going to study here is due to Floyd, and it is called the Floyd's algorithm. Okay, so now this is an algorithm that allows to allows you to compute two things. One is the length of the shortest path between every pair of vertices, okay, and then the one of the exact shortest path out of many possible. Okay, so it allows you to compute first the length of the shortest path between any pair of vertices in the graph, and then one shortest path out of the many shortest paths that are possible. Okay, this is just like the topological sort has multiple solutions. Here also, a graph, given an input graph, you can have multiple solutions for the shortest path finding algorithms. Okay, and this Floyd's algorithm that we will see is something that gives you the total length of the shortest path between any pair of vertices, as well as one of the exact shortest paths by which you can like connect two vertices with that particular length. Okay,
Sir,
shortest length. Yes.
sir, in a complete graph between any two vertices, there is only one edge. So how can we say there is n minus one path, sir?
There is one edge.
I mean,
Huh?
between any two nodes.
This is a complete graph, right?
Yes.
Okay. So how many paths are possible between this guy and this guy?
Sir, many, sir, actually.
So you said one.
No, sir, but there will be a unique path, sir, because the direct.
No, there are unique shortest paths. 1, 2. This is one shortest path. 1, 2. This is another shortest path.
Sir, but in complete graph,
Sir, won't the
there will be
shortest
an
part
edge
be
between
the
those
edge
two.
directly connecting them?
Yes, sir.
Okay, okay. Yeah, so agreed. That's an issue. Yeah, so basically, since if you have a in a graph, okay, so in a directed graph, sorry, in a complete graph, it should be there is one single shortest path. Okay, I was mistaken. Okay, so it's the direct edge between the two, but then there are multiple such cases where you can imagine that there are non-unique shortest path. Let's take this one. So between A and C, there could be, if there is no weight, then there could be two shortest paths, as you can see. Okay. So this is one example, one counter example. There could be many such counter examples. So this is actually, I just made a mistake by considering, where did that go? Yeah, it's n minus 1 paths. It's not all shortest.
So, but n minus 1 here, can we say that choosing NC2 pairs we have and each NC2 shortest paths?
actually, oh my God, what happened? We will come to this. For a complete graph, are possible.
Sir, n-1 or NC2?
N-1 factorial. Paths, these are paths. This is not NC2 edges. All paths, all possible paths. Try to calculate this. We will do this in next class, but try to do this. So there will be.
But shouldn't it be n-2 factorial?
Okay, n-2. Some order in factorial. Okay, n-2 factorial. But try to compute this. You will see this will give you an idea of the complexity of the problem if you try to do it in a brute force fashion. One way to do it is to try to see this. Believe me now, next day we will do it in details. But believe me now that there are n-2 factorial paths between a pair of any pair of nodes. Okay. Now your task would be then to find out the length of all these n-2 factorial paths and then compute the shortest among them. Okay. So you have to then enumerate all these paths and then compute the shortest among them. But then this is a humongous task, as you can understand, if you do it in a brute force fashion. Okay. And this is where the dynamic programming idea comes handy. We will see this next day, how to come up to this particular n-2 factorial paths is what we will motivate ourselves to go for a dynamic programming solution. Yeah, I'm sorry for the mistake, but I guess the idea is clear now. So you can have many graphs, even if it is, say, having weights. Then also you can have multiple shortest paths. Okay, and in fact, if this is the case, then this single edge is actually not a shortest path, even if there is a direct edge. Okay, you see this? You see this issue? Because the sum of this is 3 and the sum of this is also 3, whereas this one is 8. And our notion is that lower weight is better. So this is giving us, say, imagine that this is giving us some sort of a notion of distance between pair of cities. Okay, so therefore lower is better. Typically these type of shortest path problems come or occur in like city planning and problems like that. And therefore in such cases usually the edge weights refer to distances, and like the idea is not to find, say, a direct route with a very high cost distance, sorry, a very high cost on the path, but maybe a by route with a lower cost. Okay, that is what is the objective. So we'll stop here, and tomorrow from here onward, we will start like sketching the solution for the shortest path finding algorithm. First motivating ourselves with this n-2 factorial thing, and then proceeding forward. Okay. So the boycott is successful, right? Only 5 or 6 students in the class.
Yes, sir.